In this video, we're going to look at a few more examples of the basic comparison test. Determine whether the following series converges or diverges. Question A, summation n equals 1 to infinity, arctangent of n divided by 1 plus n cubed. Question B, summation n equals 1 to infinity, e to the power of 1 over n divided by n. Question C, summation n equals 1 to infinity, log of n squared divided by n. We have three different series, three different questions, and we have to find out whether each series converges or diverges by applying the basic comparison test. Let's look at question A first. We notice that the limit as n goes to infinity of arctangent of n, tan minus 1n, is equal to pi over 2, because this is saying what is the angle whose tangent goes to infinity. The angle is pi over 2 because tangent x has a vertical asymptote at x equals pi over 2. So arctangent of infinity is pi over 2. We also notice that tan minus 1n is monotonically increasing. So let's write that down. Tan minus 1n is monotonically increasing. Now we know that tan minus 1n is less than pi over 2 for all n bigger than 1, bigger or equal to 1. So every term of our given series, arctangent of n divided by 1 plus n cubed, is less than every term of this comparison series. So let's choose the comparison series very carefully. Let's make the numerator as large as possible. Well, we know the limit of arctangent of n is pi over 2, and arctan n is monotonically increasing, so we'll put pi over 2 in the numerator, making the numerator as large as possible. And let's make the denominator as small as possible, so that's n cubed. Notice that on the right-hand side, we have the terms of a convergent p-series with p is equal to 3, and every term of the given series is less than every term of the comparison series. So therefore, we have summation. Let's look at the right-hand side, summation pi over 2 divided by n cubed, n equals 1 to infinity. Let's factor out pi over 2, so we get pi over 2 times summation n equals 1 to infinity, 1 divided by n cubed. This is a convergent p-series with p is equal to 3. So the given series summation n equals 1 to infinity, arctangent of n, tan minus 1n, divided by 1 plus n cubed, is convergent by the basic comparison test. By the basic comparison test. So notice that every term of the given series is less than every term of a convergent p-series, and that's why we can say that the summation n equals 1 to infinity, arctangent of n divided by 1 plus n cubed, is a convergent series, because every term of this series is less than every term of a convergent p-series. Let's summarize that. Summation n equals 1 to infinity, tan minus 1n divided by 1 plus n cubed is less than pi over 2 times n equals 1 to infinity, 1 over n cubed. And on the right-hand side, we have a convergent p-series with p is equal to 3, and p is larger than 1. For this reason, this series, summation n goes from 1 to infinity, 1 over n cubed, converges. Multiplying this series by pi over 2, doesn't affect its convergence, so it's still a convergent series. So the whole idea is we made the series, the question that we were given, less than a convergent p-series, and by the basic comparison test, we can say that the given series, summation n equals 1 to infinity, tan minus 1n divided by 1 plus n cubed, is a convergent series. All right, let's look at question B. Here we have summation n equals 1 to infinity e to the power of 1 over n divided by n. Let's consider the function f of x is equal to e to the 1 over x. Now, let's take the derivative. F prime of x is equal to derivative of an exponential function is itself e to the 1 over x. Apply the chain rule to the exponent, differentiate the exponent. Derivative of 1 over x is negative 1 over x squared. This derivative is negative for all x. Specifically, it's negative for all x larger or equal to 1. That means the function is monotonically decreasing. And also notice that the limit as x goes to infinity of e to the 1 over x, bringing the limit into the exponent, we get e to the power of 1 over infinity. 1 over infinity is 0. E to the power of 0 is 1. And also, because the derivative is negative, we know that f of x is monotonically decreasing. Monotonically decreasing. So we have shown that e to the 1 over x has to be greater than 1 because its limiting value is 1 and it's monotonically decreasing. For all x larger or equal to 1. So we can now make a comparison of our series e to the 1 over n, e to the power of 1 over n divided by n is larger than 1 over n. Every term of our given series is larger than every term of the comparison series, which in this case is a divergent p-series. P is equal to 1. So this is true for all n. This inequality is true for all n larger or equal to 1. But we know that summation n equals 1 to infinity 1 over n is a divergent p-series. Divergent p-series with p equals 1. So that means the given series, summation n equals 1 to infinity e to the power of 1 over n divided by n, diverges by the basic comparison test. Because there is no space, I'll just abbreviate this, basic comparison test. So the given series diverges by the basic comparison test. So this is the idea. In this case, we made this e to the every term of our given series, e to the 1 over n divided by n. We prove that this is larger than every term of this divergent series, 1 over n, divergent p-series. And for this reason, by the basic comparison test, the series e to the 1 over n divided by n diverges. All right, so let's summarize that. So the summary is summation n equals 1 to infinity e to the power of 1 over n divided by n is larger than summation n equals 1 to infinity 1 over n. And the series on the right, the comparison series on the right, is a divergent p-series with p equals 1. Recall the theory, summation n equals 1 to infinity 1 divided by n to the p converges if p is greater than 1 and diverges if p is less than or equal to 1. Let's look at part C. In part C, we have summation n equals 1 to infinity log of n squared divided by n. Let's apply the log rule and bring the exponent down. So we have summation n equals 1 to infinity 2 log n divided by n. Let's factor out the 2 and pull it in front of the summation. So we get 2 times summation n equals 1 to infinity log n divided by n. Now we know that log x is greater than 1 when x is greater than e. So we can say log n, n being an integer, is greater than 1 when n is larger or equal to 3. And since adding or subtracting a finite number of terms from a series does not affect its convergence or divergence, we can consider summation, we can consider the index starting at 3 rather than at 1 n equals 3 to infinity, 2 log n divided by n. Factor out the 2, put it in front of the summation. 2 times summation n equals 3 to infinity log n divided by n. Now, let's form a comparison series for the series that we're given. Every term of our given series is log n divided by n. Log n is greater than 1 for n larger or equal to 3. For n larger or equal to 3. So every term of our given series is larger than every term of the corresponding comparison series, which in this case, you will notice it is a divergent p series with p is equal to 1. Now let's multiply both sides by 2, so we get 2 log n divided by n is larger than 2 divided by n for n larger or equal to 3. And we also know, and since 2 times summation 1 over n equals 1 to infinity, sorry, n equals 3 to infinity, n equals 3 to infinity, is a divergent p series. Divergent p series with p is equal to 1. With p is equal to 1. The given series summation n equals 3 to infinity 2 log n divided by n diverges by the basic comparison test. There's no space, so I will just abbreviate BCT, basic comparison test. So we can now conclude that summation n equals 1 to infinity, starting the index at n equals 1, log of n squared divided by n is a divergent series by the basic comparison test. Is a divergent series. All right, let's summarize that. That was a little bit hard, so we're going to summarize that. So we have summation n equals 1 to infinity log of n squared divided by n. The first thing we did is we applied the property of logs. We brought the exponent down. Log of x to the r is equal to r log x. So we brought the 2 down, and we have summation n equals 1 to infinity 2 log n divided by n. Then we showed that for n larger or equal to 3, log n is larger than 1. So we considered summation n equals 3. We started the index at n equals 3. So summation n equals 3 to infinity 2 log n divided by n. Then we formed an inequality, and we proved that every term of the given series is larger than every term of the corresponding p series, which is divergent with p is equal to 1. And by the basic comparison test, the given series summation n equals 1 to infinity log of n squared divided by n, notice we're starting the index at n equals 1, diverges by the basic comparison test. All right, thanks.